path length, right? So these things are discussed in the last class. Do I need to repeat that topic? What is internal nodes, what is external node, what is path length, or how to calculate
Yes,
the
madam. Yes, madam.
start from that portion. Okay, so what is 2-tree or full binary tree? A tree where each node has two child except the leaf nodes or except the nodes of the last level. So in binary tree, if the level number is L, then each level will have how many nodes? 2 to the power L nodes. This is not complete tree. That's why each node should have how many child? Exactly two child. So each level should have 2 to the power L number of nodes. So suppose this is 2 is the root node, and we always represent an internal node using this symbol, the circle symbol. And why it is internal node? Because this node has two child. One is 7 and another is 12. And the root node always placed in the first level. So here level number is 0. So this level has how many nodes? 1 nodes, because 2 to the power 0 equals to 1. Now the next level is level 1, and 2 to the power 1 equals to 2, so this level has 2 nodes. Now if we are assigning some children to these nodes, then it will be considered as internal node. So we can represent them using this circle shape. Now 7 has, suppose, 2 more children, so the level number is 2. That means here we can add 4, exactly 4 nodes. So the child node of 7 is 9, and another is 5 or 12. Okay, so we don't need to enclose these nodes in this circle shape because they're leaf node. We are not going to assign any children to those nodes, so they're leaf node. And for 12, there are 2 children. One is 10 and another is 3. So now look at this tree. Is it a 2 tree? Yes, because here all the internal nodes has exactly 2 children, and these are the leaf node, and we can call it external node. And these nodes can be enclosed in this square shape. Okay, so here now look at this tree. How many levels we used? 3 levels, and the first level is 0, 1, 2, and each level has exactly 2 to the power L number of nodes. So these are our internal nodes and these are external node. Okay, so in a 2 tree, we know that there is a relationship between the number of internal node and the number of external node. What is the relation? Number of external node equals to number of internal node plus 1. So in a 2 tree, if we are using only 3 levels from 0 to 2, then the number of internal node will be, look at the tree, how many internal nodes are here?
3.
3. So number of internal node is 3, and how many external nodes are here? 4, which is internal node plus 1. So this is true for all the 2 tree. If we are taking 4 or 5 levels here, suppose the last level is 3, so it can take 8 nodes because 2 to the power 3 equals to 8. And the leaf node always placed in the last level. So in the last level, there how many nodes are there? 8 nodes, and now this node will be considered as internal node. So now the number of internal nodes will be 1, 2, 3, 4, 5, 6, 7, and the external node is 7 plus 1, that is 8. Okay, so now here, do we know how to find out the path length? What is path length? There is a source node and there is a destination node. Now we have to find out which is the direction, or by using which path, which direction we can travel to that destination node. And we always take the root node as the source node, because here we want to find out the length of the, suppose at first we want to find out the length of the external node. So there are 4 external nodes, 9, 5, 10, 13. And if we start from the root node, now calculate the number of edges between this source node and the destination node. How many edges are here? 2 edges, because this is a path for traveling from that root node to the destination node 9. We have to start from this one. Now this is the path for reaching to this point. So in this path sequence, there are total 3 nodes, 2, 7, 9, but the path length is 2 because there are two edges between the source node and the destination node. And all these leaf nodes are placed in the same level. So it's true for the other nodes. That is, the path length is 2. Just think about the next one. What is the path length of 5? Start from 2. This is our source node. And this is the path sequence 2, 7, 5. We have to travel by using this direction. Then you can reach to this point. And the path length is number of edges between the source node and the destination node. So how many edges are here? 2 edges. So for 5, the path length is 2. And now in this way, we can calculate the path length for all these external nodes. How many external nodes are here? 4. And if we are taking their individual path length, for 9, the path length is 2. For 5, it's also true. For 10, the path length is 2. And for 3, it's also 2. So the total path length of all the external node of this tree is 8. Then what about the internal node? There are how many internal nodes? 3 internal nodes. So the path length of internal node, the first one is the root node, and the path length of the root node is always 0. Why? Because this is actually this is the destination node. And before, there are no predecessor node of 2, right? So you cannot start the journey or traversing from any other nodes because its predecessor is 0. So for 2, the path length will be 0. What about 7? This is another internal node. If we start from root node and there is only one edge, the path sequence is 2, 7. What is the path sequence for 7? 2, 7, and there is only one edge. That's why the path length of 7 is 1. What about 12? It's in the same level, so its path length is also 1 because there is only one edge. So now if we find out the summation of all the path lengths of all the internal nodes, then it will be 2. 0 plus 1 plus 1. So now can you create a relationship of this path length of the external node and the internal node? Yes, it's possible. The relationship is LE equals to Li plus 2N, and here N equals to the number of internal nodes. So Li, that is the path length of all the internal nodes, which we already got 2. And how many internal nodes are here? 3 internal nodes. There are 2, 7 and 12. So 2 into 3 equals to 6. So now 2 plus 6 equals to 8, which is equals to the path length of the external node. So the relationship between the number of nodes or number of internal node and number of external node is NE equals to NI plus 1. In a 2 tree, we'll always find if the number of internal node is 6, then the number of external node will be 7. Okay, and what about the path length? We can use this equation. Suppose only the path length of the internal node is given, then we can easily find out the path length of the external node. Just use this equation, Li plus 2N, and here N is the number of internal nodes. Is it clear?
Yes, ma'am.
Okay, so now the next one is weighted path length, because we are going to use that concept in Huffman algorithm. So what is weighted path length? We know what is path length. How many edges are there between the source node and the destination node? That is the path length. And now this edge can contain some weights. What is weight? Suppose Dhaka is our source node and suppose Chittagong is the destination. And these are two related. So this is suppose this is the edge or this is the path between Dhaka and Chittagong, and in the middle we can place suppose Kumilla. So what is the distance between Dhaka and Kumilla? Suppose 150 kilometer. Suppose 150 kilometer. And the distance between Kumilla and Chittagong is suppose 120 or 100 kilometer. Okay. So now this is the weight of this edge. In the same way, we can assign some value to these edges. Suppose the distance, this is the path length from 2 to 7, the path sequence is 2, 7, 9. So we can add some weights here, some values here. Now look at this. If we want to travel from Dhaka to Chittagong, what will be the total distance? What will be the total path length? 150 plus 100, isn't it?
Yes,
150 plus 100. Now look at this here. Between this source node 2 and between the destination node 9, there are 2 The path length is 2, but the weights of these edges are 2 and 3. So now if we add these two weights, 2 plus 3 equals to 5. That is the total weights between the source node and the destination node. But what about the weighted path length? That multiply that weight with the path length. For this node, for this destination node 9, the path length was 2. This is the path length of node 9. And what is its weight? 2 plus 3, 5. Now, if we multiply this weight with the length, what will be the total value? What will be the weighted path length? Weighted path length is 5 into 2 equals to 10. That is the weighted path length. Okay, what about the node 10? Suppose here we are assigning some value 1 and it is 4. So the total weights of the node 10 is 1 plus 4 equals to 5. But what is its weighted path length? The path length is 2. So now multiply this 2. 1 plus 4 equals to 5, 5 into 2 equals to 10. So why we need this path length? Suppose there are several ways, we will discuss these things in graph actually. There are several ways for traveling from Dhaka to Chittagong. So which one you will take? Obviously the shortest one. You will choose the H, the path sequence with the shortest length. Suppose there is another way, but if you follow that way, you need to cross, suppose, to more than 250 kilometers. So which one you will choose? Obviously the shortest one, isn't it?
Yes, ma'am.
Yeah, so that's why we need the path length. So I hope now the concept is clear to you. What is internal node, external node, how to calculate their path length, and what is the weighted path length. Weight is just we are assigning some values. That value can be kilometer. If you are calculating the distance, that when that weight can be number of bits. If we want to send the message to a network, we can consider those weight as the frequencies, how many times that alphabet, so that data is appearing in that message. So it can be anything, it depends on what type of data we are using. So now can we start Huffman algorithm, or actually Huffman code algorithm? Okay, so
Yes,
you can see
madam.
some data are given, A, B, C, D, E. These are some data. And if we think about, suppose we are sending a message, okay, and that message containing 5 characters, A, B, C, D, E. And what about their weights? Some weights are also given. The weights are, or the frequency are 5, 2, 3, 7, 6, which means that in a message, A will be appeared 5 times, but suppose we don't know which alphabet comes first. It can be B, it can be A. But for B, there will be total 2 appearance of B because its frequency or weight is 2. What about A? In the message, there will be 5A because the weight or frequency of A is 5. What about C? Its frequency is 3 or weight is 3. That means it can be appeared 3 times. What about D? It will appear in a message 7 times. And E, in this message, there will be total how many E's? 6. So now, how many characters are here? Suppose this is our message, and we can arrange these characters in any sequence. So what will be the total number of alphabets we want to send? Just calculate the weights or frequencies. 5 plus 2, that is 7. 7 plus 3, 10. 10 plus 7, 17. 17 plus 6, 23. Now, suppose this is Huffman code algorithm. That means we have to encode these characters. After that, the receiver needs to decode the characters. What is encoding? Now, this Huffman algorithm will help us to create a minimum weighted path length. So why we need that? The appearances, how many times the characters will appear in a message it's given, because these are its weight or frequency. Okay, so now think about these alphabets A, B, C, D, E, how these alphabets can be coded. There are some coding schemes, Unicode, ASCII code, isn't it? So how we usually code or extended binary coded decimal, there are so many forms, right? So how we can encode this sequence A, B, C, D, E, or each of these character. Think about Unicode. In Unicode, how many characters are used for representing one character? How many bits are needed? In
20.
In Unicode 20, no, 16.
16.
Right.
Yes.
So 16 is a, look at this. We have to use 2 to the power 16 bits, so it's not possible. Okay. So think about ASCII code. How many bits are needed for encoding one character in ASCII code? Previously we used 7 bits, but we now actually use 8 bits. 8 bits. In ASCII code, we use 8 bits for representing one character. That means in ASCII coding scheme, we can represent how many symbols? 2 to the power 8, that is 256 symbols. If we use ASCII code, then how many characters can be encoded? Total 256. I mean 0 to 255, total 256 characters. Right. That means if we want to send a message in, and if the message belongs to this message belongs to the this characters belongs to that message, then how many bits we actually need for sending all these bits, all these 23 bits. Each character needs how many bits? 8 bits. That means 23 character needs how many bits? 23 into 8. Now calculate it. It will be a huge number, 23 into 8. But why you use Huffman code algorithm? For creating a minimum weighted path length. That means if we use this algorithm, it will provide a variable length code. What is variable length code now? Suppose if we are using ASCII coding method, how many bits are needed for encoding one character? 8. And do you know what is the ASCII value of this capital A? What is the ASCII value in ASCII coding scheme for each of the character, for all the digits, all the symbols, all the characters, all the letters or alphabets, there are some value. What is the value of this A? What is the ASCII code of B? For capital A, the ASCII code is 65, and for small a, lowercase a, the ASCII code is 97. Right. So look at this. If we are using ASCII coding scheme, that means this 65 needs to convert it into binary, and how many bits we will use for representing the binary number? Exactly 8 bits. That's why the total number of bits are needed for sending these messages, 23 into 8. That means for representing each of these character, how many bits we need? 8 bits. But that is, and look at this, if we are using 8 bits, that means in our table or in our chart or in our tree, there can be how many characters? 256 different characters. But here, how many characters we are using? Only 5, A, B, C, D, E. So do we need to use actually 8-bit length fixed code for encoding each of these characters? No. So this Huffman code algorithm will provide us a variable length code, where maybe for representing, for encoding A, we need 2 or 3 bits. For representing B, maybe we need 2. It depends on the path length of that character in the Huffman tree. So is it clear what is the main concept of Huffman code algorithm? We will try to create a minimum weighted tree, or we will try to create the variable length code for each of the character. So now how to create that tree? I already told you, every time we have to take 2 characters with minimum weight. So at first we can do one thing, we can organize the data according to their weights in ascending order. So here B has the smallest weight, that is 2. At first we'll take this one. Okay. So B2, or if you want, you can write the weight first to B, and you can use this square shape because these are leaf node. And then which one has the lowest value? C, and its weight is 3. So this is the second. And then the next one is, which one will be represented next?
5.
A, because its weight is 5. So this is A, and then the next one is E, and its weight is 6. Last one will be D, and its weight is 7. Okay, so why you are using this Huffman algorithm? For creating a Huffman tree, where every time we will take 2 characters with smallest weight. So now look at the sequence. In this sequence, all the data are arranged in ascending order. So we'll always get the lowest data item in the left side. So now if we take these 2 nodes with the weight 2 and 3, how we can, these are external nodes, how we can create the internal node? By adding their weight. So 2 plus 3 equals to 5. So now this will be an internal node, and how we got this internal node? After adding 2 data with smallest weight. So one is B with weight 2, and another data is C with weight 3. So now after creating a new tree, an internal tree, now how we can again organize the data in a sequence. We are storing the data in ascending order. So now we already took these two data and then we created this internal node 5. And for 5 the left child is B because its weight is 2 and the next one is C. Okay, so now this is our sequence. 5 is the internal node and how many external nodes are left? 3, 5, 6, 7. So if we want we can take 5 before this internal node 5 or after internal node 5 because their values are same. So the next node is 5 and then 6, after that 7, or actually these 7 are the number of appearances or frequency or weight of those character D. That is, in that message D will be appeared 7 times. Okay, so now we can find out two characters with minimum weight, and you have to also check whether after adding these two numbers what will be the result, or is there any options to take the characters. I mean, if we take these two characters 5 and 5, what will be the value of the internal node? 5 plus 5 equals to 10. Now we can check this two external node. If we add these two nodes, the result will be 5 plus 6 equals to 11. Or if we take these two nodes, one is internal and another is 7, 5 plus 6 equals to 11. So which one you should choose? Obviously that's two nodes which will create another node with smallest weight. So 5 plus 5 equals to 10, we will choose this one. So now after adding these two nodes, this will be another internal node 10, and the left child of that 10 is this one, the internal node, or you can take the actually external node. So if you want to take external node, then in this sequence we can place that external node before this internal node. So 5A. And now the left child of that internal node 10 is A, and the right child is in internal node 5, which is composed of two external nodes. One is B and another is C. Okay, so now again organize the data. So here these two external nodes value weights are less than this internal node, so we can add them before this internal node. This is 6 and another is 7. So now these are three data items. One is D with the frequency or weight 6, another is D with 7, and then this internal node 10. So now how we can, again, we are compressing the data, isn't it? We are trying to compress the data, and initially we had 5 data items, now we have 3 data items. So now which 2 data items will be chosen? If we add these 2 internal nodes, what will be the weight of the new internal node? 6 plus 7 equals to 13. So is there any way to get another internal node with height less than 13? Just consider this two. 6 plus 10, 16, no, it's greater than 13. Then 7 plus 10, 17, it's also greater than 13. So now we will take these two nodes, 6 and 7. So after adding these two nodes, the weight of the new internal node will be 13. That means 10 will be, and this is a node 10, and where we can store the next node after 10, and its weight is 13. The left child of 13 is 6, and E with weight 6, and another is D with weight 7. Okay, so now after this compression, how many nodes we have? Only 2 nodes, isn't it? That means we can take these 2 nodes now for creating another internal node. So 10 plus 20, 10 plus 13, what will be the value? 10 plus 13, 23, isn't it? So we can add these 2 nodes and their weight will be 23. And now look at the value of this root node. The weight is 23, and after adding all those weights we got exactly 23. But at that time, how many data external nodes we had? 5 external nodes. Now in this tree, the total weight of all these external nodes are 23, and whenever we are using that distinct node or this individual node, we need how many codes for sending each of these digits? 8 codes. Now this Huffman tree will, or by using this Huffman algorithm, we can generate some variable length code. How to generate that variable length code? Now look at this tree. This Huffman algorithm allow us to set a 0 in the left child. Suppose 10 is the left child of 23, add 0. This external node A is left child of 10, add 0. Whenever you get a left child, just assign its value 0. And 13 is the right child of 23, so assign 1. And this D is the right child of 13, so assign 1. And if it is left child, then assign the value 0. This 5 is the right child of 10, so its value will be 1. We are assigning some weights, or we can call it code. And this C is the right child of 5, so we'll assign 1. And for this left child, the value will be 0. After creating a Huffman tree, now assign some values to each of the edges. If the node is left child of the root node, then assign the value 0. Or if it is the right child, then assign 1. Okay, after that, our main purpose is to create a variable length weight for all these external nodes. How many external nodes we have? 5 external nodes. And initially we had to use 8 bits for sending each of this message, and the total number of bit was 23 into 8. But now look at this tree. In this way, after assigning some values, how we can generate a variable length code. So the external nodes, how many external nodes are here? 5. For A, what is the path? This is the path sequence. From 23 to 10, 10 to A. Okay, so in this path sequence, which values are assigned? 0 and 0. So this 0, 0 is the variable length code for A. And now the next one is B. And what is the path sequence of B? 23, 10, 5, and then 2. And what is the path length? Path length is 3. So in these 3 path lengths, we assigned 3 value, 0, 1, 0. So for B, the variable length code is 0, 1, 0. But in that way, when we are using, or when we are sending this individual bits, characters, we have to use how many bits? 8 bits. But now look at this. For A, the length of the variable code is 2. And for B, there are only 3 bits. Okay, and what about C? For C, the variable length code is 0, 1, 1. For D, this is the path length for B. Sorry, this one is D. This is the path length, and we assign the value 1, 1. So 1, 1 is the variable length code for D. And the last one is Z. What is the variable length code for E? 1, 0. Okay, so now look at this. How many bits now we need for sending these characters? For sending A, we can use only 2 bits, and its path length is also 2. Okay, for B, we need to use 3 bits. For C, 3 bits. For D, 2 bits. And for E, 2 bits. Now look at their weights or frequency. The frequency of A is 5. That means in that message there will be total 5A. And if we need 2 bits for sending 1A, then for sending 5A we need how many bits? 2 into 5. Look at this. This is the weighted path length. This is the length that we are considering as code now, and this is the weight of that character. So this is the weighted path length 10. For sending A in this message, we need how many bits? 10 bits. What about B? The appearance, the weight of B is 2, and each character B needs how many bits? 3 bits. So multiply the length or weight with its length 3. 2 into 3 equals to 6. Now the next one is C. For C, the path length was 3, and we assigned 3 values in this path length. So the code for C is 0, 1, 1, and the code length or length is 3. Now multiply these 3 bits with its weight. So 3 into 3 equals to 9. What is the weight of D? The weight of D is 7. Okay, and how many bits? Each character D needs 2 bits. For sending 1D, we need 2 bits. So for sending 7D, we need how many bits? 7 into 2 equals to 14. And then what about the last one, E? E needs 2 bits and its weight is 6. So 6 into 2 equals to 12. Now add all those in, because we have to find out the weighted path length for all the external nodes of the tree. So 10 plus 6, 16, 16 plus 9, 25, 25 plus 14. 39 plus 12, 51. So now the total amount of bits are needed for sending all these characters are 51. But when we are using 8 bits code for representing each of these characters, we needed how many bits? 23 into 8. So is it clear why we're using Huffman code algorithm? For compressing the data size as well as for reducing the bit. In this way, by using Huffman code algorithm, we can construct a minimum weighted path length tree. So this is the total amount of bits that are needed for sending all the characters of these frequencies or weights. Is it clear what is Huffman code algorithm?
Yes, ma'am.
What about the others? Is it clear?
Yes, ma'am.
So you can try. I'm giving you some characters with weights. You can create the tree as well as you have to find out how many bits are needed. Okay. So these are the data items. And the weights are okay. So these are the data with their weights. Now you have to construct a Huffman tree as well as you have to find out how many bits are needed. So look at this data item. How many data items are here? 6 data items. And in ASCII coding scheme for encoding each character, we need how many bits? 8 bits. And look at the weight of these characters. How many in the message? If we construct that message first, then in that message there will be total 4b, 2e, 12f, 9g's, 7d's and 3a's. So total number of characters is 4 plus 2, 6, 6 plus 12, 18, 18 plus 9, 27, 27 plus 7, 34, 34 plus 3, 37. And then if you multiply that character, total character 37 with 8, then you'll find out how many bits are needed. But using Huffman code algorithm, you can reduce the bit size. You can create a compressed tree. Okay, so now create the Huffman tree as well as find out total number of bits that are needed for sending all the characters. Okay, just try to create the tree.
2E.
Very good. E. And what is the weight of E? 2. Okay. Now the next data will be A. Okay, and its weight is 3. And the next one will be B, and its weight is 4. Then the next data item is 7, and its weight is, the next one is D with weight 7, and then G with weight 9, and the last one is F with weight 12. So in this message, what are the total number of nodes? How many characters are here?
6.
Actually, in the message, what are the total number of characters? Not 6. 6 types of character we have taken, but what are the total number of characters in that message? You have to add.
37 into it.
No, I'm only talking about the characters. The total number of characters, 37. The total number of characters is 37. Okay, and in this Huffman tree, we'll compress all the data, then we'll get only one whole tree, and that root node will be 37. Okay, and for sending the whole message, for sending 37 characters, we need how many bits? 37 into 8. Now use the calculator. What will be the value?
296.
296. Okay. So now we'll find out whether by using this Huffman tree algorithm can you reduce the number of bits. Okay. So what is the process? At first take two characters with smallest weight, that are E and A. After adding these two numbers, what will be the value of the internal node? 2 plus 3 equals to 5. And the left child of 5 is E. And the right child of 5 is A. Okay. So now again organize the nodes in the sequence. So now before 5 or before this internal node, can we store any other nodes? Yes, that is B, because the weight of B is less than 5. So here we can take 4B, and after 5 we can take this 9 and 12, G or D, G and F.
Madam, how do you get 5?
After adding the weight of this two tree, what is the process? Take two minimum weights node and add them for creating a node, an internal node. So 2 plus 3 equals to 5. And how these nodes are created? After taking these two characters. That's why these are the child node of that internal node. Okay, so now look at this sequence. Now the next step is we have to choose two nodes with smallest weight. So which one we should take? If we take these two nodes, 4 plus 5 equals to 9. So is there any way of creating a node with weight less than 9? Just take two other nodes, 4 plus 7, that is 11, or 5 plus 7 equals to 12. So it's not possible. So now the smallest two nodes are B and this one, the internal node 5. After taking these two nodes, now we can create another internal node. 4 plus 5 equals to 9. So 9 is the weight of the new internal node, and its left child is B with weight 4, and its another child or right child is another internal node 5. And this 5 also created from two external nodes. One was E with weight 2, and another node was A with weight 3. Okay, so now again we can organize the data in ascending order. So now this is a node with weight 9. So we can place 7 and 9 before this internal node. So now one node is 7 or D7 and another is G9. And then the last one is 12. F with the weight 12. Okay, so we are trying to compress, we are trying to create a minimum weight restricted path length tree. So now take two nodes with minimum weight. So if we take these two nodes, then the result will be 7 plus 9 equals to 16. Or if we want, we can take this two node, 9 plus 9 equals to 18, but 16 is less than 19, so we will add this two node. So now after adding this two node, this will be the ascending order sequence. At first we will take the internal node 9 with this two external node B, and this is 5 with two external node E and A. Okay, so after adding that two node, what will be the value? 7 plus 9 equals to 16. So we can take 12 before that 16 because we are organizing the data in ascending order. So now 7 plus 9 equals to 16 and its internal node. So we'll use this circle shape, and 16 now has how many children? Two children. One is 7 or D with weight 7 and another is G. So what is the next step? The next step is take two nodes with smallest weight to create another internal node. So if we take this two node, then the weight of the new internal node will be 9 plus 12 equals to 21. And if we add this two node, 12 plus 16, it will be
28.
12 plus 16, 28. Which one we will choose? Obviously, we will take this two nodes. 9 plus 12 equals to 21. So now after compressing this two node, we can create one node. And the weight of that node will be 9 plus 12 equals to 21. So this is 21, and this node has how many child? Two child. Its left child will be 9 and the right child is F with weight 12. And now 9 has two children. One is 4 and another is 5. This is the external node, right? So 4B, and 5 has two children, B and E and A. Okay. So now where we can place 16? Before 21 or after 21? After creating another internal node, now look at the sequence. How many nodes are left? Two nodes. One is this internal node 21 and another is this 16. So 16 is less than 21, we can place it before 21. 16, and it has two child, D and G. So what is the next step? Now this sequence has only two character or two nodes, so we can simply add these two nodes. So after adding this two nodes, what will be the weight of the internal node? 16 plus 21, that is 37. So now look at this. For those external nodes, we just created a new node, that is 37. And this is our Huffman tree. Look at this here. The total number of characters in that message was 37, and we just created a Huffman tree where the root node is 37. What is the next step? Now after creating the Huffman tree, now we can assign the values because we have to find out what is the variable length code of these characters. So what is the process? Just add 0 to the left child of any node. For 37, the left child is 16, so assign a value 0. And this D is a left child of 16, so here you can assign 0. And G is a right child of 16. In the right side, we'll add 1. Again, 21 is the right child of 37, assigning the value 1. For 21, the left child is 9, here we'll add 0. And B is the left child of 9, here we can add 0. Now 5 is the right child of 9, add 1. And for 5, E is the left child, where we can assign 0. And here we will assign 1. Now F is the right child of 21, so we can assign 1. After assigning all these values, now we can find out the code of each of these characters. Okay, so now the first character is here D, or we can take B first. Okay. What will be the code for D? The length of D is 2, isn't it? What is the path sequence for D? 37, 16, and then D. So this is the path sequence of D. Okay, so how many codes we have assigned here? The level, the path length is 2. That's why we assigned 2 bits. So the variable length code of D is 0, 0. Now the next character is G. What is the variable length code of G? Its path length is 2. That's why we assigned 2 bits in each of these path length. So one code is 0, another is 1. This is the variable length code for G. What about B? The path length of B is 3. That's why we need 3 bits in each of these level. So the variable length code for B is 1, 0, 0. This is the path for reaching to this point B. So 100 is the variable length code for B. Now the next one is E. What is the variable length code of E? 1010, because its path length is 4. That's why there are 4 bits. 1010. And what about A? Its path length is also 4, so we need 4 bits here. 1011, that is the variable length code for A. What about the last character F? Its code is 1, 1. Okay, so now here for representing D, we need 2 bits. Here the bit length is not fixed because we are using variable length coding. In this way here, when we used ASCII code at that time, the bit length was 8. It was fixed. For encoding each of this character, we need 8 bits. That's why the total number of characters we need for sending all these characters in that message is 296. But here we used variable length code. The bit length depends on actually the path length of each of this character. Now we can find out the total number of bits that are needed for sending all these characters. So what will be the total amount of bits are needed for D? The weight of D is 7. That means in that message there are 7 D. For sending 1 D, we need 2 bits. So for sending 7 D, how many bits we need? Calculate its weight at path length. Now its weight is 7 and its path length is 2. And now we are considering each of these bits in the path length. Okay, so now 7 into 2 equals to 14. This is the total amount of bits are needed for sending all the Ds. And for G, the bit length is 2 because its path length was 2. So we need 2 bits for sending 1 G. What is the weight of G? 9. For sending 9 G, we need how many bits? 9 into 2 equals to 18. What about the next character B? For sending 1 B, we need 3 bits. And there are how many Bs are there? 4 B. So 4 into 3 equals to 12. We need total 12 bits for sending 4 Bs. What about E? For sending 1 E, we need 4 characters. And here, there are total 2 E. Suppose this is our message. And in that message, there are how many E? 2 E. For sending this 1 E, we need to use this code 1010, 4 bits. For sending the second E, we need this 4 bits, 1010. So the total amount of bits are needed is 4 into 2. That is 8 bits. What about A? For 1A, we need 4 bits. And how many A's are there? 3 A's because its weight is 3. So 3 into 4 equals to 12. What about F? We need 2 bits for 1 F and there are total 12 F. So 12 into 2 equals to 24. Now we have to find out the total number of bits that are needed for sending all the characters. Now add all these values. 14 plus 18, 32, 32 plus 12, 44, 44 plus 8, 52, 52 plus 12, 64, 64 plus 24. $88, right?
Yes, madam.
So now look at the difference. When we are using ASCII code, I mean fixed length code, we needed 296 bits, but here we need only 88 bits for sending all the characters, and that is the main purpose of using Huffman tree, for reducing the bit size as well as to compressing the data size. So that is the end of the chapter 3. So in 3, we discussed how many topics. At first, we started with some terminologies of tree, and then we talked about some types of tree: binary, general, full binary tree, then complete tree, and then what was the next topic? Tree traversal. How to traverse the binary tree. There are three ways: in order, pre-order, post-order. Then how to construct tree from their traversal sequence. And then we discussed about some sorting techniques, right?
Yes,
And
ma'am.
then BST, binary search tree. That is, what is binary search tree, how to construct binary search tree from their sequences, or how to traverse the binary search tree. And then the next topic was heap tree. What is max heap or min heap, how to add nodes in max heap tree, or how to delete nodes from the max heap tree, and then heap sort algorithm. Now the last topic was Huffman code. Okay, so in the next class we will start graph. But before that, in our tomorrow's class, I'll give you an assignment. In tomorrow's class, I'll give you an assignment, and that assignment value is 20. It's a 20 marks assignment, and you have to submit the assignment within 17. The due date submitting the assignment is 17. Okay, so I'll give you the content or topic of the assignment in tomorrow's class. Clear?
Yes, ma'am.
Clear?
So now please response. 1,
Yes, ma'am.
2,